All right, so let's carry on with the PAC learning that we started last session. So we mostly talk about the probability distribution of your x's, so your observations or random variables that we have in the training examples, and how we're going to relate the statistical analysis of those in training sets with respect to test sets. So we talked about in-sample error and E-out as well, so as your test error. And we were trying to analyze the relation between these two parameters, right? So we talk about a bin of marbles containing two set of colors, red and green, and then we wanted to see if the probability of having red in the marbles represented by mu here can be related to the V as a fraction of red marbles we sampled from that test case. And we call the fraction of red marbles in a sample in-sample error, so the error associated with that, and those available in the bin which are out of the sample, we call them E-out or the test error, right? And we were talking about generalization, so we mentioned mu is unknown. How are we going to relate these two, right? So we pick n marbles independently, and later on we talk about how we're going to relate mu and v here. And then again, we talk about the relation between these two. So I posed two questions. First, I ask, does V say anything about U at all? So the answer was no, because the samples you take from the jar of or the bin of marbles could be completely representative of another probability. Could be close, could be completely different. And we said that it's likely they're close to each other. Also, we mentioned roughly that if you have a big sample, so n goes towards infinity, we probably be close to mu within a margin epsilon. So now in this session, we're going to talk about how we're going to quantitatively define this margin and how we're going to relate these two. So we're going to talk about mostly two inequalities. One is Hoeffding's inequality. The other one is Russian scientist Chebyshev's inequality. All right. So now let's recap again. So we are trying to relate E out and E in here. So the probability of the function z equal to 1 is mu, right? And we mentioned that mu is unknown. So now, what exactly is this function z? In this case, we define z as 0 if green was drawn from the bin, and it's going to be 1 if red was drawn, right? So this function returns either 0, 1, and they are random variables. So in a statistic, we call this function z the Bernoulli distribution. So this is R. So when we say z comes from a Bernoulli distribution of mu, is that z represents 0 and 1 for the case that one of the items was picked and the other case representing otherwise, right? And the probability involved with that is going to be mu. So we represent it this way. Z comes from a Bernoulli distribution with the probability of mu. Okay? So now, let those be n independent draws, right? So this represents only one draw. But how about we make this n independent draws? with the outcome that we don't know, right? They are representing with mu. So in this case, if you want to represent this for, so that was for a single draw. This will be n independent draws, right? N times. So you're going to have Z1, Z2 up to Zn, and all of them are coming from the Bernoulli distribution, and all of them are identically independent distribution. We talked about it in previous session. So they are independent from each other. So this IID represents that. So now, when we have n of those draws, how are we going to relate our mu and v here, right? So basically, this session we're going to talk about this. Okay, as an example, so let's assume mu is equal to 0.6, and we have 9 independent draws, right? So 1 to 9. Number 1, number 9. So you see each of these could be either 0 or 1. So the output sequence will be represented by, in this case, 1, 0, 0, 1, 1, 1, 0, 0, and 1. Right? So now we can define v of n, that v represented before, in this case, by n draws, as the summation of all those z's, all those zeros or ones, divided by their number, right? Intuitively. And we define this to be the estimate of the mu after n draws, right? So we had this for one draw. If we have it for n draws, so we can define v of n as 1 over n, the summation of i's from 1 to n, zi for n draws. If we plot this, so your x-axis represents your n, so from 1 up to n, which was 9, and the y-axis pertains to y of n, and this is the maximum, which is 1. This is 0, right? So all of them are in this range. Either that's the window of their v. So you see that if you plot this based on their, based on the mu here, so you're going to have something like this, and that was your mu representing here, right? So you see that more or less these random variables representing your test case, right, in the output sequence, you see that they are mostly around the mean that you had, right? Probably in a window here, right? But the window here is way smaller than the overall window that represents the whole variation of v. So now one might wonder how we're going to relate these two, mu to v, right? If these ends goes towards infinity, very large number, are we going to affect this window? Is it going to be diverging, converging, or if these two are unrelated completely, right? Okay, so let's talk about some of the properties of the Vn we just described. So as you know, Vn is a random variable. That means this comes from a random distribution, could be independent from each other. And we can define the mean of that. You remember last session we were talking about this E for out of sample error as expected value. So E of Vn on n draws, we can represent it as E for n times 1 over n summation of i's from I to 1 to n zi, right? And assuming that this expectation of zi for n as a large number is mu, the final result of expected value of this becomes mu itself. Likewise, for a random variable, we can define the variance. So the var of Vn on the other side. So this is the mean. This is the variance. Would be the variance of n draws, 1 over n summation of i's from 1 to z. And if you take a look at the random variable formulas, the variance of the random variable, if you don't want to relate it to the mean, you can define it like this: 1 over n squared variance of summation of n's i's from 1 to n, zi, and this would be 1 over n of var z. So this is the properties of random variables for variance, mean. And this number is always smaller or equal to 1 divided by n. So these two properties are known to us because Vn is a random variable. Now, so we can infer the fact that Vn goes closer to mu. So the mean of the test cases, the test examples, is going to go towards the mean of the training examples, which was mu, as our n, the number of samples, goes to a very large number, right? Thus, we can define it as this way: the probability of the norm of the absolute value of Vn minus mu. So this represents E out. This was representing E in, right? So the error associated with estimating training examples, the error associated with estimating test examples. So these were the probability of these two, right? So as n goes to a very large number, these two converge to each other. These two goes close to each other. So the probability of these two, the difference between these two in an absolute way, is going to be more or less within an epsilon value, right? Let me check what I've missed here. All right. Okay. And this one also close to 0, right? As n goes to infinity to a very large number. So we can define the Vn within this range, right? So if this was your mu line, just like the previous example, so we can expect that the Vn would be around this value, minus e, mu minus e, or mu plus e, right? In this range. And we are sure that this will happen because the probability of this is going to be 1 as n goes to a very large number. Mapping that to the previous example, so you had 9 draws and the mu was 0.6, so we can say that Vn is around this window with this threshold, right?
So is that just saying that as you do like more and more trials of the Bernoulli experiment, the outcome is going to be equal to the average?
They are going close to each other, right? That's right. Okay, now let's just put all this together and come up with a new rule or a new inequality. So we call it Chebyshev's inequality. It basically defines that the absolute deviation of a random variable from its mean will exceed a given threshold, right? So this inequality provides an upper bound to all the probabilistic models. So say Vn was defining as 1 over n, the summation of I1 up to n, zi, and the variance of n is smaller or equal than 1 over n. So we can define the probability of Vn minus mu greater than epsilon is always equal or smaller than the variance divided by epsilon square, and this value itself is is smaller or equal than 1 over n, which was the number of samples, divided by epsilon square as well. So this defines an upper bound that the absolute deviation of a random variable from its mean will exceed a given threshold, right? That was the threshold here. So we can use this now to quantitatively quantize actually and define the exact window that your Vn and mu are different from each other. All right. Now, using this inequality, if you recall it, the Gaussian model that I was talking about, and I was talking about their mean being the maximum value here, and you're expecting that the variance would be this window, right? Plus and minus epsilon. And I was talking about the confidence levels that we can define in our random distribution. So using Chebyshev's inequality as well, this shaded area here on the left and the right side of the mu plus epsilon and mu minus epsilon are representing us a new variable. We call it delta as our confidence level. So the probability of this, it will be equal to the area of the shaded region, right? So the area corresponding and defined by delta here is going to be the equal value of the probability of Vn outside this window, right? It means that here or there, these two sides. And this is a very important thing in a statistical test because we can understand how robust a distribution is by calculating its confidence levels. So we call 1 minus delta confidence level, and these intervals, we call it confidence intervals. So you might have heard of student t-test in a statistic. So when you have different generation of experimental result and you want to make sure how robust they are they coming from the same distribution, are they different? So you normally apply a student t-test like with confidence level of 95%, right? So this comes orthogonal to this. The higher the confidence level is, the better your distribution was generated, or the more robust you have. So you can say these distributions are coming from same source. So now if delta is given to you, say 1%, 5%, 10%, you can define the confidence intervals using that delta. Normally in t-test they set it to 5%, so they're interested in if your distribution was passed with 95%, more or less they call it robust. Okay, so let's see an example. So delta is 1%, 1, 0. So the confidence intervals or the confidence level becomes 99%. So we can calculate this. Delta would be 1 over n sigma square, epsilon square, or the root square of 1 over n delta, changing these two. And then if you calculate the epsilon using that delta, it's going to be 10 divided by root square n. So now if you have the mu here, if you have the mean of your generation, you can define your confidence intervals. So CI, I abbreviated here. So you can define the confidence intervals of 99% as this, because this is the mu plus the delta, mu plus the epsilon, and this is mu minus the epsilon, right? And this region is going to be called your confidence interval with 99%. Okay. You've already saw Hoeffding's inequality in the fourth lecture. I'm just going to bring it up again to have a complete set of lectures here. So this inequality represents an upper bound again and relates your V's on a large N, so we can call it also Vn. So we call it in a big sample large N, Vn is probably close to mu within epsilon again. And that was the probability, so PR or P, either case. So the Vn minus mu is going to be within a threshold epsilon, and this value is smaller than 2 exponentials minus 2 epsilon square n. So note that this is a minus negative exponential, and in another word, if you define PEng, the definition of PEng is the statement mu equal to V is PEng, and PEng represents probably, approximately correct, right? So when we talk about PEng learning, we are trying to relate mu with V, and we say mu could be equal to V, probably approximately correct. Okay, so let's define it using a Bernoulli distribution. This is probably double L. So again, Vn was defined as 1 over n, the summation of all the z's, and zi's were coming independently from Bernoulli distribution with the mean of mu. So we could define Hoeffding inequality just like the previous slide. So this is the exponential decrease in n because we have minus here, right? And let's relate delta to this value as well. So we can call delta this value, Thus, if you want to define epsilon with delta, so you just have to switch these two, and this becomes a root square. So the square of 1 over 2n log of 1 over delta, right? Okay, let's see an example of this when we have delta again as around 1%. So if delta is 0.01, so it's 1%, we can calculate epsilon as 1 over 2n log of 100, right? Thus epsilon would be this value, 1.63 divided by the root square of n. Using that, we can define also the interval and relate the mu to Vn with a parameter n, right? So this area would be the mu plus your epsilon, and this would be mu minus your epsilon, right? So now all we talked about today by now is when we have a high number of n, so n is a large number, but we have one test and training example. Say we have one bean of marble, like bean number 1. In the next session, we're going to talk about if you have multiple beans, so bean up to n, and each of them has their own mu and v, right? Now, how are we going to define different mu's to different vn's in a generalization case of Hoeffding's inequality, right, for multi-beans? And that's going to be your final session of the PEng learning before we start VC dimension and other techniques. Any questions? All good? Okay, so see you guys on Friday.